In section 5.3, what we're going to look at is special factoring. We're going to specifically look at factoring binomials. And what are binomials? Well, if we're looking at factoring binomials, the key or root word there for bi is two terms. Okay, well, we're going to only look at two main cases. We're going to look at where we have what's called a difference of two squares. And by difference, we mean we're subtracting. And by squares, what do we mean by squares? We mean things like 25 or literally x squared. And what we'll do, and the easiest way to kind of go through this is to look at an example, is let's say if I had x squared minus a good square is, let's see, 9. Is to say, well, it's a difference first. That's how we know we're going to be okay doing it, is that it's a difference. And then we'll look at the first piece and say, what's squared? Well, an x is squared there. And the 9 is a 3 squared. So let's see, how is that going to factor? What this formula tells us is that we'll factor into two pieces, two binomials, both of which will have the x as their first part, and both of which will have the 3 as the second part. But with the difference of squares, what it tells us is that one will be a plus, and the other will be a minus. And the reason why that works out is you can really see it if you FOIL it out. Multiplying out the x first, you'll get a x squared minus 3x. Multiplying out the 3 second, you'll get a 3x minus 9. And what you'll notice happens is that negative 3x and positive 3x cancel. That's why you need one as a plus and one as a minus, so that those inside terms cancel out. But then what happens is, on that last piece, when you multiply the 3 and the negative 3, you get a negative 9. That's why it has to be a difference of two squares. It is the only way to get a negative or a difference is if you have one that's a plus and one that's a minus. So this rule only works if you have a difference of two squares. Let's take a look at A. In A, we've got x squared minus 144. Again, this is set up for being squares because we do have a difference or a minus sign in the middle. The question would be, what is squared in each piece? Well, we've got an x that's squared in the first piece, and then what do we square to get 144 is just a 12. So when we factor this out, we've got a difference of two squares. We've got an x and a 12 in both slots. And the formula told us that in order to get a negative here, we need a plus and a minus. And that will also make sure that those inside terms cancel out as well. But that's it. Our final answer is x plus 12 times x minus 12. And it doesn't matter if you put the one with the plus first or the one with the minus second. It won't matter. Let's take a look at B. In B, we have something slightly differently going on. If we look, we've got a 64 and a 16. Before we do anything, they're both divisible by quite a bit. You could actually say 8, but they'd still both be even. There's something even bigger than 8 that you could pull out as a greatest common factor before you do anything. They're actually both divisible by 16. So let's factor out a 16 first. So 16 will go into 64 4 times, and we'll still have our x squared. And 16 will go into the 16 once, so we'll just end up with the minus y squared here. Notice, whenever we can, we've talked about this before, we want to always factor out the greatest common factor, which in this case was 16. Now I need to make sure I don't lose it, so I'm going to keep it out in front. The question is whether or not I can go ahead and do my squares now that I've pulled out the greatest common factor. So you'd look at your 4x squared and you'd say, what can I factor out? And you've got a 2 and an x. because what's squared to get your 4 is a 2. What's squared to get your x squared is a x. And what's squared in your second piece is a y. And we do have a difference, which is what's required for squares. So we're perfectly set up. So we can factor this out into our two pieces like we have in the past couple. We'll have a 2x and a y and a 2x and a y. Remember that one of these will have a plus in the middle and one will have a minus, but that is all. And that is our final answer. But notice, we would not have been able to do this the same way, nor would it have been factored correctly had we not pulled out the greatest common factor first. Let's take a look at C. On C, let's see what we have. We do have a difference. We're thinking that they're squared because both exponents are divisible by 2. So let's take a look. What do we have that's squared in the first piece? Well, we can square a 5 to get the 25. The question is, what do you have to square to get the x to the 4th? Well, you actually have to square, you need 2 x squareds. What do you need 2 of, or to square to get the y to the 4th is a y to the 2nd. So we can indeed break this up using the difference of 2 squares. Again, you'll get 2 binomials. The first piece in each will be the 5x squared, and the second piece in each will be a y squared. And because of the minus, we're going to always have one's a plus and one's a minus. It does not matter which order you put them in. And that's our final answer. Let's take a look at D. In D, we've got 32x squared minus 2y squared. And what do we notice? Is they're both divisible by 2. And we'll factor out a 2. And let's see how that helps us, if anything, because we have to do our GCFs first. When we have a 32 and a 2, they're both divisible by 2. And if I go 2 goes into 36, 16 times, I'll still have my x squared minus the 2 will be gone from the second term, and I'll just have the y squared. The question is whether or not I can now do the squares on this leftover piece. Again, just like before, we do not want to lose the 2 that's out in front. So let's go ahead and copy that down. And let's factor out our 2 squares if we can. So what is squared to get this 16? X squared is a 4 and an x. So that'll be our first piece in both. And what's squared in our second piece is just a y. And remember, it is okay to do a difference of squares for this one because we have that minus sign in the middle. And what that means is it'll break down into one's a plus and one's a minus, but that's our final answer. Again, we want to be careful to not lose that 2 out in front that we factored out first. Let's take a look at E. In E, we have x to the 4th minus 16. Again, we have a minus sign in the middle, so we're all set up for possibly being able to do this. The question is, what's squared, or do you need 2 of to get the x to the 4th? Well, you need 2x squareds, or you need to square an x squared to get an x to the 4th. What's squared to get 16 is a 4, so that means that this will factor out into 2 pieces as an x squared and a 4. An x squared and a 4. One will be a plus, and one will be a minus. However, something weird just happened. We have squares again. We've got an x squared, and we've got a 4, which is a 2 squared. So the question is, can I use squares again? And you can and can't. Remember, we said our rule was for a difference of squares, not a sum or a plus. So the one with the plus, we actually can't do anything with that, so I'm going to leave that as is, x squared plus 4. However, the second piece, the x squared minus 4, is a difference of 2 squares, and I can break that down. And what is squared in the first piece is an x. What is squared in the second piece is a 2, so it'll break down as an x and a 2. Just like before, one will be a plus and one will be a minus. Now notice that this time we don't have any squares in the x and the 2, so that's how you know you're done. At most, you'll be able to do the squares twice like this, but you'll only be able to do it on one of the pieces a second time, not both, because you can only do it on a difference of squares. But numbers that do this a lot are things like, let's say 16, because then it breaks down into 4 and 4, which can be broken down again into 2 and 2. Another good one is, let's see, 81. 81 breaks down into 9 and 9, which is another square of 3 times 3. Another perfect one that most people forget about is the number 1. 1 can be broken down into 1 times 1, which is still a square because it can be broken down into another 1 times 1. So you have to be careful and just kind of keep thinking about things. Okay, let's look at one that's a little bit trickier. Let's look at F. We've got x to the 6 minus 9. What's squared in each term? Well, what's squared in the first term is an x cubed, because I need 2 sets of 3 x's to get an x to the 6th. Again, when you're looking at squares, you're saying, what do I need 2 of? I need 2x to the 3rds to get an x to the 6th. What do I need to square? I need 2 of to get a 9 is a 3. So what does this mean when I factor out my difference of squares, which I can because it's a minus sign, is remember that that means is that they'll both have an x cubed and a 3 in that order. It's just one will have a plus and one will have a minus. And that's it. Notice I'm not worried about the x cubed because it's not a square, so I don't have to worry about breaking that down again. Let's take a look at the last one, G. On G, we have an x squared plus 16. Yes, the x is squared. Yes, the 16 is 4 squared. There is a problem, though. The problem is right in the middle. We've got a plus. We said that our rule only works if you have a difference or a minus sign. So we looked at a plus sign earlier and we said you can't do it. And that's going to be the same here, is whenever you see a sum of squares, it actually cannot be factored. And what do we say when something cannot be factored? There's a special word for it. It's that it is prime.